Hello students, welcome to Max Benny. In this video, we are going to solve question number 15 of exercise 20.1. Question is, find the regular function whose imaginary part is given. Regular function means analytic function. So we need to find an analytic function whose imaginary part is already given. First we are solving the first question, which is imaginary part is x minus y divided by x square plus y square. It is we need to find f of z. F of z is equal to u plus I v. V is the imaginary part. V is already given here. It is x minus y divided by x square plus y square. So we need to find a function f of z which is analytic with the imaginary part x minus y divided by x square plus y square. So here we use Milne-Thomson method. That is, here f dash is equal to ux plus ivx. We can write f dash z is equal to ux plus ivx. We find an analytic function f. So u and v satisfy CR equation. So ux is equal to vy plus I Vx. Instead of Ux, we write Vy. Then we can calculate Vy and Vx using this V, and integrating with respect to z gives the function f of z. So Milne-Thomson method, here we use Milne-Thomson method to find this analytic function f of z, which is equal to, by Milne-Thomson method, f of z is equal to integral of vy, instead of x we put z, and instead of y we put 0. That is, in Milne-Thomson method, x is equal to z and y is equal to 0. Put x is equal to z and y is equal to 0. So that we get the function f of z, which is analytic. Vy of z0 plus I into Vx of z0 dz. So, integrating f dash z by putting x is equal to z and y equal to 0 with respect to z. So, we need to find Vx and Vy. So, V is there, Vx is equal to V with respect to x. It is in the form u by v. So, denominator into derivative of numerator with respect to x, that is 1, minus numerator into derivative of denominator with respect to x, that is 2x, divided by denominator square, x square plus y square whole square. Thus Vx is equal to x square plus y square minus 2x square plus, here minus and minus will be plus 2xy divided by x square plus y square whole square, which is equal to x square minus 2x square is minus x square plus y square plus 2xy divided by x square plus y square whole square. Now we need to find Vy with respect to y, and this denominator x square plus y square into derivative of numerator. V is equal to x minus y divided by x square plus y square. Numerator into derivative of, denominator into derivative of numerator with respect to y, that is minus 1. Minus 1 minus numerator into derivative of denominator with respect to y is 2y divided by denominator whole square, x square plus y square whole square. It is minus x square minus y square minus 2xy plus 2y square divided by x square plus y square whole square, and which is equal to minus x square 2y square minus y square is plus y square minus 2xy divided by x square plus y square whole square. So this is Vy and Vx already we have. So f of z is equal to integral of Vy of z0. So Vy is here. Put x is equal to z and y is equal to 0. That is minus z square divided by z square whole square plus I into Vx z0. Vx is here. Put x is equal to z and y equal to 0 gives minus z square divided by z square all raised to 4. Yes, I minus z square divided by z raised to 4 dz. That is z square cancel. We have minus 1 by z square plus I into minus 1 by z square dz. Z square cancel. So integrating with respect to z. Minus 1 by z square integrating with respect to z gives 1 by z plus I into 1 by z plus integrating constant c. The derivative of 1 by z is minus 1 by z square. So integral of minus 1 by z square is 1 by z plus I into 1 by z plus c. So this is the function f of z. Or we can write it as 1 plus I divided by z plus integrating constant c. So this is the function f of z. Second question is minus sin x sin hy. That is imaginary part is minus sin x sin hy. So V is equal to minus sin x sin hy. We need to find the function f of z, which is equal to integral of Vy at z0 plus I Vx at z0 dz. So we need to find Vy and Vx. Vy with respect to y, that is minus sin x is constant. Sin hy derivative with respect to y is cos hy. Now Vx minus sin hy is constant. Sin x derivative is cos x. So Vx and Vy we have Vy of z0 is minus sin z cos h0. Cos h0 is 1. Vx at z0 is minus sin h0 cos z. Sin h0 is 0. So Vx is 0 and Vy is 0. Vy sin z minus sin z. F of z is equal to integral of minus sin z dz, which is equal to sin z, integral of sin z is minus cos z. So minus minus cancel. So minus of minus cos z plus c, that is cos z plus c. So f of z is cos z is the analytic function. Third function is e raised to x into sin y. Imaginary part is e raised to x into sin y. So v is equal to e raised to x into sin y. So we need to find an analytic function f of z. By Milne-Thomson method, integral of Vy at z0 plus I into Vx at z0 dz. Vy is integral with derivative with respect to y. E raised to x is constant. Sin y derivative is cos y. Cos y. So Vx is e raised to x derivative is e raised to x itself. Sin y is constant. Now Vy at z0 is e raised to z cos 0 is 1. Vx at z0 is e raised to z sin 0 is 0. That is 0. So f of z, analytic function f of z is equal to integral of e raised to z dz. E raised to z is integral e raised to z itself plus the constant c. So this is the analytic function f of z, e raised to z. If you want to verify, let's check e raised to z. E raised to z is e raised to x plus iy. You know that z is equal to x plus iy is the complex number. So we can write this as e raised to x into e raised to iy. And this is e raised to x. E raised to iy is cos y plus sin iy. Sorry, cos y plus I sin y. E raised to iy is cos y plus I sin y. So, e raised to x cos y plus I into e raised to x sin y. So, e raised to z is an analytic function with the real part e raised to x cos y and imaginary part e raised to x sin y. So, e raised to x sin y is the imaginary part of real analytic function e raised to z. So, here the f of z is equal to e raised to z plus the integrating constant, let it be 0. So, v equal to e raised to x sin y is the imaginary part of analytic function e raised to z.